Yo, welcome to Physics with Vinay. In this lecture, we're going to be talking about electrostatics. So first off, charge. We know there are two types of charges, positive and negative. Identical charges repel each other, opposite charges attract each other. So Coulomb's law, the basis of electrostatics, I have, let's say, Q1 and Q2 charge, and they are at a separation of R. So the force between them is given by K Q1 Q2 by R squared. And if I were to write it in vector form, so let's say I have R vector, which is the position vector of particle 2 with respect to 1. So the force on 2 by 1 would be K Q1 Q2 by R squared R cap. So R cap will denote the direction of the force vector. And this force is a central force. The central force is basically that the force is always directed towards or away from a fixed point, and it is only dependent on the distance between the two charges. So for example, in this particular situation, force by charge 1 on 2 is always directed away from 1 if they are identical charges, or it will be always directed towards charge 1 if they are opposite charges. Then the force will be attractive. So central force is conservative, and conservative force means, we've seen this in our work per energy chapter. Conservative force is a force whose work is independent of the path taken from one point to another point. And for conservative forces, we can define potential energy. So here the potential energy between these two particles is K Q1 Q2 by R. Here we make the assumption, or we make the choice, that potential energy is taken to be 0 at R tending to infinity. So this is a choice. You can set a potential energy to be 0 at any other point, but this is the standard convention and mathematically the most convenient choice. Here K is 1 by 4 epsilon naught. Epsilon naught is called the permittivity of free space, and its value is 9 into 10 raised to 9 Newton meter squared per Coulomb squared. Alright, so let's look at a question based on Coulomb's law. Let's see what kind of a question can come. Alright, so here we have a charge 1 coulomb placed at the origin, another charge of 4 coulombs placed at 3, 0, and these charges are fixed externally. The question is asking, find the location of a third charge for it to be in equilibrium. So I need to find where should I place the third charge so that the net force on that charge is 0. So the way we will do this question is, one thing that you have to realize is that the third charge is going to be between 1 coulomb and 4 coulomb. It cannot be to the left of 1 coulomb, because if the third charge is positive, both 1 and 4 will repel it. If third charge is negative, both 1 and 4 will attract it. Similarly, same reasoning for if the charge is on the right hand side of 4 coulomb. And therefore that charge, third charge, has to be between 1 coulomb and 4 coulomb. So let's say that distance is x. This will be 3 minus x. And what I'll do is I'll just balance out the forces. So if the third charge is positive, then 1 coulomb will repel it and push it and apply a force to the right. 4 coulomb will also repel it and apply a force to the left. So we can just balance out the magnitudes of the forces. So you will have the force by 1 coulomb on charge q would be, using Coulomb's law, k into 1 into q divided by x squared should be equal to k into 4 into q divided by 3 minus x the whole squared. So basically I'll have 3 minus x the whole squared is equal to 4x squared. So 3 just takes the square root right away, be 2x, and therefore x would be equal to 1. So I would like to place the charge at 1, 0, and that will ensure that it is in equilibrium. Another thing that the question can ask is, so what is the nature of this equilibrium? Whether is it is a stable equilibrium or unstable equilibrium. Let me just go to the next page. So I have my third charge at a distance of 1, 0 that we already found out on the previous page, that will be in equilibrium. Now let us assume that, let me take first case, that the charge is positive. So it is undergoing repulsion by both 1 coulomb and 4 coulombs. Now if I were to slightly displace this charge to the right, so this charge will experience a force by the 4 coulomb and a repulsive force by 1 coulomb. At 1, 0, the charges were applying the same force on Q. Both 1 coulomb and 4 coulomb were applying the same magnitude of force on Q. Now, if I push this charge to the right, you should be able to see, because in Coulomb's law the force is inversely proportional to r squared, you should be able to see that the repulsion by 4 coulomb will increase and repulsion by 1 coulomb will decrease, and therefore the net force will be to the left. So if you displace it to the right and the net force is in the opposite direction, then of course the equilibrium is stable. So for a positive charge, the equilibrium is going to be stable. What if the charge is negative? In that case, you should be able to see that it will be the opposite of what is happening when the charge is positive, because the negative charge is in equilibrium at 1, 0 and it is undergoing attractive forces from 1 coulomb and 4 coulomb. Now, if you displace it slightly to the right, it is going to experience an attractive force by 4 coulomb to the right and an attractive force by 1 coulomb to the left. Once again, because the charge is now going closer to the 4 coulomb, the attractive force by the 4 coulomb will increase and the attractive force by the 1 coulomb will decrease, and therefore the net force will be to the right. So once you displace it to the right and the net force is also to the right, that means it is unstable equilibrium. Now you have to realize, and this question may have arisen in your mind as well, that why are we only considering displacement along the x-axis? And that is a perfectly correct question. In the exam, if you encounter this, the question will have to specify that we are considering displacement only along the x-axis, because in theory you should be able to displace it in any direction and check the equilibrium. Now let's do that on the next page. Let's displace it parallel to the y-axis and let's check the equilibrium. So once again, I am taking the first case that the charge is positive. So I have 1 coulomb, I have 4 coulomb, and this positive charge is, let's say, displaced along the y-axis. So you should be able to see that this charge will get repelled by the 1 coulomb and it will get repelled by the 4 coulomb as well. And therefore, it should be very clear that the net force is going to be away from the equilibrium position. This is unstable equilibrium. Remember, we are displacing it by very small amount. So we can say that the x components are cancelling out. The resultant will be along the y-axis. And in the second case, when the charge is negative, it's just going to be the opposite. You displace the negative charge and it is going to get attracted by 1 coulomb and 4 coulomb and it is going to come back to its original position, and therefore this equilibrium is going to be stable. So what is happening here is that for the positive charge, if you displace it along the x-axis, the equilibrium was stable as we saw on the previous page, but now if you displace it parallel to the y-axis, the equilibrium is coming out to be unstable. Overall, such an equilibrium is called unstable. Remember this, it's very important. For an equilibrium to be called stable, it should be stable in every possible direction. If there is even a single direction along which the equilibrium is unstable, then overall we term it as unstable. So here overall the equilibrium position is unstable for both positive and negative charge. In electrostatics, what happens is that it is actually impossible for a charge to be in stable equilibrium position in all directions due to electrostatic forces. We'll talk about this in one of the later lectures after we study the concept of Gauss law. Overall, let me just write that down. Overall, the equilibrium is unstable. Let's take a look at another question. Suppose I have a charge Q here and I have a charge minus Q, and both are free to move, and the left charge is initially at rest. Let's say mass of both charges is the same. So they have the same mass, but same charge in magnitude, but opposite in sign. So this right hand side charge is given a velocity v naught initially. Along the line joining the two charges, let's say the initial distances are. The question is asking us to find the minimum value of v naught such that the distance between the two charges becomes infinity. So I want to find the minimum speed of minus q such that the distance between the two charges becomes infinity. So a little bit of mechanics combined with electrostatics here. You'll have to think what all quantities you can conserve. So if you want, you can pause the video and give it a try, and then you can take a look at my solution. Okay, so the best way to do this would be to go to the center of mass frame. Now first of all, let's just calculate the velocity of center of mass in the ground frame, which would be the left is released from rest and the right has a velocity v naught. So the formula was m1 v1 plus m2 v2 and so on divided by total mass. So m v naught for the right hand side charge divided by total mass is 2m, so this will v naught by 2. Now in the center of mass frame, you should be able to see that because in the ground frame the center of mass is moving to the right. So in the center of mass frame, this charge q would be moving to the left with the speed v naught by 2, and similarly minus q will be moving to the right. I've just done relative velocity. Now you should be able to see that q and minus q will attract each other, and therefore they will both keep on decelerating, and eventually we want a situation where the distance between them becomes infinity. So we want them to just reach infinity. So their velocities should just become 0 finally, and the distance becomes infinity. So once again, I can just conserve energy from the initial to the final situation. So the initial kinetic energy is half m v naught by 2 the whole squared for both the particles. So I am multiplying it by 2. And what about the potential energy? That is minus kq squared by r. Now here some students may have this doubt that I am writing potential energy only one term, even though I have two particles, and I am writing kinetic energy, I am multiplying the kinetic energy by 2 for two particles. So what's the issue? Potential energy is defined for an interaction. Now this is something that you learnt in work per energy chapter. Potential energy is not defined for a single particle, it's always defined for an interaction. So one pair of particles, one pair of q and minus q, one pair, and therefore one interaction, and therefore one term for potential energy only. Do not write two terms separately for these two charges. Their interaction is one interaction, and therefore it's one potential energy term. Alright, so the potential energy initially would be minus kq squared by r. Finally, because the distance is infinite, potential energy would be how much? 0. And what about the kinetic energy? They are both, the speeds are both 0, so kinetic energy will also be 0. And that's it. Therefore, you will get your speed as root of 4 kq squared by mr. So this was a pretty good level question, combining the concepts from mechanics, combining it with electrostatics here. Let's do one more question. Let's say I have a charge q here, and it is given a velocity v naught. And I have another charge q which is fixed. Let's say this distance is b. The mass of the charge that is given an initial velocity v naught, the left charge, and the mass is m, and it is given a velocity v naught at infinity. So this distance initially is infinite. So what will happen is, the left hand side charge will undergo Coulomb repulsion by the fixed charge, and it will go something like this. So I want to calculate the minimum distance between the charges during the motion. So you should be able to see that the distance between the two charges will keep on reducing. This blue lines that I've drawn are the distances as the left charge travel. And at one point, the velocity of the moving charge will be perpendicular to the distance between them. That is when the distance will be minimum. After that, you should be able to realize that after that, once again, the distance between the two charges will increase. Alright, so this V is an unknown here. So I have two unknowns basically. I have this minimum distance and I have the velocity at that minimum distance. So I'll need two equations. So think in terms of mechanics, think in terms of what you can conserve. Pause the video and give it a try. Okay, so the quantities that we can conserve here is, one is of course energy conservation and the other is angular momentum. Why can we conserve angular momentum? Because the force on this moving charge will always be going through the fixed charge. These are the force directions on the moving charge as the charge moves. So you can see it's all the force, the line of force is all going through this fixed charge Q. And therefore, the torque of the force about this fixed charge Q would be 0. And therefore, angular momentum will be conserved. So let's write the equation. So let me first write angular momentum conservation. So the angular momentum conservation, initially the angular momentum would be the momentum times the perpendicular distance, which is B. So m v naught b, and finally it would be m v r. This angle is 90 degrees. This is one equation. And the other equation is energy conservation. So from the first equation I get my velocity as v naught b by r. And energy conservation, what is the initial energy? Half m v naught square. What is the initial potential energy? 0, because the distance is infinite between the two charges. Finally, what is the potential energy? Kq squared by r plus what is the kinetic energy? Half m v naught square b squared by r squared. And this will be my second equation. Alright, so let's just solve this these two equations. I'll do it on the next page. So my equation was half m v naught square is equal to kq squared by r plus half m v naught square b square by r squared. This was my equation. So let me just multiply by r square everywhere. I want to convert it into quadratic. Basically, you should be able to see that. So I'll have half m v naught squared r squared should be equal to kq squared times r plus half m v naught squared b squared. I've just multiplied by r square the entire equation. Let me just divide by half m v naught square also. So I'll have r square minus 2kq square by m v naught square r minus b square is 0. So this will be my equation or quadratic for r. And now it's just a quadratic equation. So r would be equal to 2kq squared by m v naught square minus 4ac, so plus 4 b squared divided by 2, and there should be a square here, of course. Alright, so here we know that r is positive and therefore we will select the positive sign in the quadratic, and therefore my final answer, I'll just write it as kq squared by mv naught squared plus, let me just take the 2 inside the square root, the denominator 2, and that will be kq squared by mv naught squared plus b squared. So this will be my minimum distance between the two particles. Now let's talk about electric field. So if I have any object or any charged object and I want to find the force on some let's say q dash, let's call it test charge. So I'm placing that q dash charge and I'm trying to find the force by the charged object on q dash. So whatever force I get, force on Q dash, if I divide by Q dash, that is what we get as the electric field produced by the charged body. So the electric field by the charged body is only dependent on the charge of this body. And the reason we define this electric field is because it makes force calculations very convenient. So for example, if I, in front of this body, if I were to place, instead of Q dash, if I were to place some other charge, so I don't want to again calculate the force by integration on the new charge. Instead, if I calculate the electric field produced by this charged body, then I can immediately say that the force on Q dash is nothing but Q dash times the electric field produced by the charged body. Charged body being this body. So whatever Q dash you use, all you need to do is multiply it by the electric field. So once we have calculated the electric field, we can calculate the force between that charged body and any other point charge. And that is the whole mechanism and the convenience of defining electric field in the first place. So for a point charge, Q at a distance r, I will write down my electric field as kq by r square r cap. So this is what the electric field of a point charge comes out to be. You can see if Q is positive, then the electric field at this point will be pointing away from the point charge. So for positive charge, the electric field lines are pointing all away from the point charge. These are all my electric field lines. And if charge is negative, you can see electric field will be negative r cap in the same direction as negative r cap. So that means the electric field will be pointing towards the negative charge. Now let's look at the first example in this chapter. Let's just revisit that. So you should remember that the first example, 1 Coulomb, 4 Coulomb. 1 Coulomb was at the origin, 4 Coulomb was at 3, 0. Now we found that if you place a third charge at 1, 0, that is the equilibrium position. The force on that third charge is 0. So that third charge is actually placed at a point where the net force is 0 by 1 Coulomb and 4 Coulomb. That also implies that the net electric field by 1 Coulomb and 4 Coulomb is 0. Let's just also do it by basics. So let's say at a distance x, if I want to write down the electric field. So let's say I'm taking x-axis towards the right as positive. So my electric field due to 1 Coulomb, remember 1 Coulomb and 4 Coulomb are positive, so electric field will be radially away. So due to 1 Coulomb, electric field will be towards the right, and due to 4 Coulomb, electric field will be towards the left. So I'm writing the net field to the right. That will be due to a point charge. Just quickly recollect what the electric field we had gotten it as. Kq by r square was the magnitude. In vector form, it is kq by r square times r cap. So here I will write k into 1 Coulomb divided by x squared, and E4, that is electric field due to 4 Coulomb, this distance would be 3 minus x. So that will be k times 4 divided by 3 minus x the whole square. Should be a negative sign here. Alright, so this is the net field to the right. And if you want to find the equilibrium position for an external third charge, just set the net field to be 0. And you will get the same equation that we had gotten while solving the first example in this chapter, and you will get x is equal to 1 as we had also gotten in that question. So x equal to 1 is the equilibrium position as we had already seen. And now let us say I want to plot this electric field. So this is also kind of question that can be asked. They can ask you to plot the electric field as a function of x along the x-axis. So let's just do that on the next page. So I have electric field, 1 Coulomb here, 4 Coulomb here. So I'm plotting the electric field on the y-axis here in this graph. So first off, the best way to plot these electric fields is you have a couple of points of interest. So right hand side is positive. Now remember, a point charge, when it is positive, the electric field is radially away. So the electric field will be all radially away from the positive charge. So just to the right of 1 coulomb, my electric field will be to the right because it is radially away from the positive charge, and the magnitude will be tending to infinity because R is very close to 0, because you are looking at a point that is very close to 1 coulomb. So very close to 1 coulomb on the right hand side, the electric field is tending to positive infinity. I am taking right hand side as positive, so electric field is to the right and it is tending to positive infinity. So my graph will start off at positive infinity. Now, what about very close to 4 coulomb? Just to the left of 4 coulomb, the electric field will be to the left, because once again the field by this positive charge will be away from the positive charge. So the electric field will be to the left, and once again in magnitude it will be tending to infinity because the electric field is very close to infinity, because R is very close to 0. So the electric field will be tending to negative infinity. Negative implies that the electric field is to the left. So my electric field will be somewhere here, and therefore my graph would be something of this sort. The point where the graph cuts the x-axis will be the position where the electric field is 0. That is the equilibrium position, which we already found out as x equal to 1, where 4 coulomb was x equal to 3 and 1 coulomb is at the origin. Now let's also plot the graph in the other regions. Just to the right of 4 coulomb, the electric field will be away from 4 coulomb because it's once again positive charge. Electric field is radially away and very close to 4 coulomb, so it will be positive. So we're tending to positive infinity. So my graph will start off here, and very far away from both the charges at positive infinity. At infinity, the electric field due to 1 coulomb and 4 coulomb both will be 0. So therefore, the graph, the electric field will be tending to 0 as we go very far away. Similarly, if I look at the region to the left of 1 coulomb, just to the left of 1 coulomb, the electric field will be to the left away from 1 coulomb, so it is in the negative direction, and magnitude will be infinity, so the electric field will be tending to negative infinity. And once again, very far away from both the charges, the electric field has to tend to 0 again. So this will be the graph of electric field. I hope you've understood how to plot the graph. Now you can actually use the graph to also check the nature of stability. We already saw how we judge the stable or unstable equilibrium along the x-axis, but let's just look at it from a graph point of view. So we had, let me just quickly draw the graph. So this was my graph, 1 coulomb, 4 coulomb electric field. Now this x equal to 1 was my equilibrium position. What is the slope there? The slope is negative, so that means dE by dx is negative. Now if I were to place a third charge there, Q, the force on that charge would be Q into E. Now you should be able to see that dF by dx will therefore be equal to Q times dE by dx. Now if the slope is negative, that is dE by dx is negative, then if I look at the case where charge is positive, that will imply that dF by dx is also negative, and this is the condition for stable equilibrium position. You must have learned this in work per energy chapter. And similarly, if Q is negative, dF by dx will be positive, and that will be the condition for unstable equilibrium. So this is what we had gotten by just displacing the particle and checking the force direction when we had done that problem, the very first problem in this chapter. But I hope you've understood how to check the nature of stability from the graph as well. Alright, let's do a similar type of problem. So here I have just changed the sign of the 1 coulomb charge. Now it's minus 1 coulomb, and you have 4 coulomb at 3, 0. Now the question is first asking us to locate the position on the x-axis where the electric field is 0, and then you plot electric field versus x. So I would suggest that you try it out, pause the video, try it out, and then you can have a look at my solution and see if you've gotten the correct answer. Alright, so let's first figure out the location of the point. Now, I have three regions here. One region is to the right of 4 Coulomb, one region is between -1 and 4, and the other region is to the left of the -1 Coulomb. So first you should be able to figure out in which region will this equilibrium position lie. If I look at a point that is on the right hand side of 4 Coulomb, the magnitude of the force, remember, is inversely proportional, or magnitude of the electric field rather, is inversely proportional to r squared. So you should be able to see that the 4 Coulomb electric field here will be greater than -1 Coulomb magnitude wise, because the blue point is closer to 4 Coulomb compared to -1 Coulomb. So of course the electric field magnitudes will never be equal, so electric fields will never cancel out. So that region is eliminated. We cannot have an equilibrium position to the right of 4 Coulomb. Next, what about between -1 and 4 Coulomb? Here as well an equilibrium position is not possible, because the 4 Coulomb will have an electric field away from itself, and -1 Coulomb will have an electric field towards itself. So clearly both electric fields due to both charges are in the same direction, of course, so how will they cancel out? So this region is also not possible. So that leaves us with only one region, which is to the left of -1 Coulomb. So to the left of -1 Coulomb, let's say this length is L, where the electric field is 0. So let's write down the electric field. So electric field due to -1 Coulomb, it will be towards -1 Coulomb. So electric field due to -1 Coulomb, let me call that E1. And electric field due to 4 Coulomb will be away from 4 Coulomb. Let me call that E4. So my net electric field should be 0. So E1 and E4 in magnitude, these are magnitudes, should be equal. So can I write electric field due to -1 Coulomb would be, remember electric field was kq by r squared. So in magnitude I'll have k1 by L squared. Remember this is magnitude, so that's why I'm using 1 Coulomb, not -1 Coulomb. Should be equal to the magnitude of the electric field by 4 Coulomb. So k times 4 divided by L plus 3 the whole squared. So once again I'll have L plus 3 the whole squared is equal to 4L squared. Take the square root right away. L plus 3 is 2L, and therefore I will have L is equal to 3. So 3 meters to the left of -1 Coulomb is where you will get the position of 0 electric field. So the coordinate would be -3, 0. So this is the point where electric field due to both charges result in a 0 value. Now let's plot the graph of E versus X. Alright, I have -1 Coulomb, I have 4 Coulomb, and I'm going to plot the electric field on the y-axis. Alright, now let's start off with the rightmost region. Just to the right of 4 Coulomb, my electric field will be away from 4 Coulomb and it will be tending to infinity. So I'll start off with positive infinity. Very far away from both charges, the electric field once again has to go to 0. So this will be my graph. Now between -1 Coulomb and 4 Coulomb, let's go to a point which is just to the left of 4 Coulomb. Once again the electric field will be away from 4 Coulomb and it will be tending to infinity. So electric field is to the left, that means it is negative infinity, and very close to -1 Coulomb. Just to the right of -1 Coulomb, the electric field will be towards -1 Coulomb. So it's again to the left, so negative infinity once more. So I'll have this sort of a graph. Now you can ask me why or how do we know whether the graph will cut the x-axis or not? The graph will cut the x-axis only at the equilibrium position where the electric field is 0. We saw that electric field is 0 only at -3, 0. So here between -1 Coulomb and 4 Coulomb, the graph is not going to cut the x-axis. Finally, let us come to to the left of -1 Coulomb. So just to the left of -1 Coulomb, the electric field will be towards -1 Coulomb. So it's to the right and very close to -1 Coulomb. So it's positive infinity. So we'll start the graph off from positive infinity. Now, here we found out that the electric field is going to become 0 at -3, 0. So at -3, 0, x is equal to -3, the electric field is becoming 0, so the graph should cut the x-axis there. And ultimately at negative infinity, Once again, you're very far away from both the charges, the electric field will again go to 0 because the electric field is proportional to 1 by r square. As r tends to infinity from both the charges, the electric field will go to 0. And therefore, the graph will have to curve back up and tend to 0. So all of this has been deduced by looking at points very close to the charges and that one equilibrium position. I hope you've understood how to plot the graph. Here, you can use the graph to check the stability of a third charge that is placed at the equilibrium position, like we did in the previous example. So what you can do is you can pause the video right now, check the stability, and then check the stability for both cases where charges, the third charge Q is kept at x equal to -3, and the cases where Q is positive and Q is negative. Check both cases, and then you can take a look at my solution. Alright, so for Q positive, see, we already know the slope here is positive. So for Q positive, df by dx will also be positive, and therefore that equilibrium is unstable. For Q negative, df by dx is negative because slope is positive and charge is negative. So that will be stable equilibrium position. Notice that by displacing this point charge, we will not be able to judge the equilibrium like we did in the very first question in this chapter. When the equilibrium position was between 1 Coulomb and 4 Coulomb, that was very easy to judge. In this case, we'll have to plot the graph and check. Or the other way is to write the force, or rather write the electric field as a function of x and then differentiate to get the slope. The reason we cannot just check by displacing the charge is because just imagine you displace this charge slightly to the right. The force by both -1 Coulomb and 4 Coulomb are going to increase. -1 Coulomb will attract if that Q charge is positive, and 4 Coulomb will correspondingly repel. But both -1 Coulomb and 4 Coulomb force is increasing as you move the charge to the right. So we don't know the direction of the net force, and that is why we plotted the graph in order to check the stability. Now let's look at the electric field due to some continuous charged configurations. So first thing, let me take a circular arc. Suppose I have a charged circular arc, and let's say the charge density is uniform. So let me define lambda as the charge per unit length. So it's the linear charge density, and it's a constant. So the field at the center of curvature of this circular arc, and let's say this angle is alpha, the field is along the bisector. Now this field line will be directed away from the arc if lambda is positive, if it is positively charged, and it will be directed towards the arc if it is negatively charged. And this field by symmetry, you should be able to see that it will be along the bisector, and the magnitude of this field comes out to be 2k lambda by r sine of alpha by 2. So for example, if you have a semicircle and you want to find the force, let's say you want to find the force between the semicircle and this point charge Q kept at the center. Let's say this radius is r. So the force will simply be Q times electric field, and the electric field would be 2k lambda by r. And what's the angle? The angle is 180 degrees. So alpha is pi. It will be sine alpha by 2. So pi by 2. So 2k lambda q by r. So it's very straightforward. In order to calculate force between semicircle and point charge, or any circular arc and a point charge kept at the center, just make sure that you remember the electric field. Next, let's look at a line wire. So for a line wire, so this red line is my finite line wire whose electric field I'm going to write at point P. So let me take, this is my x-axis, and let's say this is my y-axis. And let's say the perpendicular distance from point P to the line wire is r. So my electric field x component comes out to be k lambda by r sine alpha plus sine beta, and the y component comes out to be k lambda by r cos alpha minus cos beta. Just remember that we've taken this as my orientation for x and y axis. So for example, for an infinite wire, you should be able to see that both alpha and beta will tend to pi by 2. So only the x component of electric field will remain, as expected by symmetry, and that will be equal to 2k lambda by r. So this is a standard formula that we have to remember for infinite wire. Now one very important point to note is, if I just label the ends of this finite wire as A and B, and you have point P here, this angle is alpha, this angle is beta. So in this diagram, we have taken alpha as the angle subtended by A at P with the perpendicular from point P to the wire. So alpha will be positive if A is above P, and therefore alpha will be negative if A is below P. Similarly, beta is positive in our diagram if B is below P, and therefore beta will have to be taken as negative if point B is above P. Now what I mean by that is, let me just give you an example, it will be clearer. So suppose I have point P here. I drop a perpendicular from point P on the line. So the line wire is actually only from A to B. I've just extended it upwards. Let's say this perpendicular distance is R, and let's say this angle is 30 degrees and this angle is also 30 degrees. Now I want to write the electric field. Let me take X and Y axis this way, and I want to write the components of the electric field. Now A is below P. You can see that from the diagram, correct? A is below P, and therefore my value of alpha, remember alpha has to be measured from the perpendicular. Alpha and beta both have to be measured from the perpendicular. So alpha would be minus 30 degrees. This is the crucial point. Alpha is less than 0 if A is below P, and in this example that is the case. So alpha is minus 30 degrees. And what about beta? Beta is below P, but below P, that means beta is positive. So will I take beta as positive 30 degrees or positive 60 degrees? I'll have to take it as positive 60 degrees. Why? Because we are measuring once again from the perpendicular. So this entire angle would be beta. I hope you've understood this. So beta would be plus 60 degrees. And then you just substitute alpha and beta in your expression for the electric field. You can do that on your own and you can get the XY components. I hope you've understood how we were able to figure out the sign convention for alpha and beta. This is a very crucial point. So I hope there is absolutely no doubt here. Let's just look at one more example for you to practice on. I'll go to the next slide. Alright, so here we have a line wire whose uniformly charged and charge per unit length is given to us as lambda, and these angles are 15 degrees and 30 degrees. And the question is asking us to find the electric field at point P, which is at a perpendicular distance of r from the line wire, and the XY axis are given to us in this manner. So find the electric field vector, so in I cap, J cap components. Give it a try and then you can have a look at the solution. Alright, so I'm going to label these points as A and B, the uppermost and the lowermost end of the line wire, and now you can see that A is above P, and therefore that means that alpha is positive, and therefore I'll take alpha as this entire angle from the perpendicular is going to be alpha. Remember, we measure it from the perpendicular, so alpha is going to be equal to 45 degrees, positive 45 degrees. What about beta? Here point B is above P. So that means that beta has to be negative. Once again, from the perpendicular, this angle is 30 degrees. So beta would be equal to negative 30 degrees. And now you just have to substitute it in your formula that we had derived. So Ex was equal to k lambda by r sine alpha, sine 45, plus sine beta. So this would be equal to k lambda by r 1 by root 2 minus half, and Ey would be k lambda by r cos alpha. So cos alpha is cos 45 minus cos beta. So cos of minus 30 is simply cos 30. So this will be your x and y components, and you can just write down E vector as Ex I cap plus Ey j cap. That will be your final answer. Now let's look at a very interesting property that this electric field by a line wire, by a finite line wire possesses. It has to do with the direction of the electric field. What happens is that at any point, the net electric field bisects the angle subtended by the endpoints. So these two blue angles here, they are equal. The entire angle, see, remember my line wire is to subtend an angle of alpha and beta. So this entire angle here is alpha plus beta. So each of these angles here would be alpha plus beta by 2. So I'll prove this on the next page, but just this fact is something that we would like to remember, that the electric field is along the angle bisector. So for example, in the question, if they ask you something of this sort, that you have a line wire and let's say this is 60 degrees, find the direction of the electric field at this point. So very simple, the electric field will bisect and therefore it will make an angle of 30 degrees with the perpendicular. Now let's look at the electric field due to a ring. So electric field due to a ring on its axis. If this radius is r and let's say the charge on the ring is q, my electric field at a distance x from the center of the ring will come out to be kqx divided by r square plus x square raised to 3 by 2, something that you should remember. Or later on we'll see we can derive it from by differentiating the potential of the ring as well. We'll talk about the potential of the ring later on, so you can use that as well. But I would suggest that you just remember it's a standard formula that is applicable many times in questions. So just remember this formula. And if I plot the electric field versus x, there comes out to be a maxima. And that maxima comes at x equal to r by root 2. You can just differentiate this electric field and calculate the location of its maxima. And of course, by symmetry, the electric field is along the axis of the ring. It will be away from the ring if the ring is positively charged, and it will be towards the ring if the ring is negatively charged. Here I've assumed that we have uniform charge distribution. If the ring had non-uniform charge distribution, then this quantity that we've gotten would actually be the x component of electric field. And an easy way of looking at this is once again by differentiating the potential on the x-axis, and we'll talk about that later on when we talk about potential of the ring. The y component in the case of non-uniformly charged ring may be non-zero. I should say y and z component. This is my x-axis. So yz plane will be parallel to the plane of the ring. So the yz component may be non-zero depending on the charge distribution, but the x component will still be given by this equation. Now let's look at an example. Let's say I have a particle at the center of a ring, and let's say in the first case we take the ring as fixed. Later on we'll just allow the ring to be free to move as well. So let's say this particle at the center of the ring is being given a small displacement along the axis of the ring. So I want to find the time period of small oscillations. So if I displace the point charge by x, my force on it would be the point charge q times the electric field, and the electric field was kqx divided by r square plus x square raised to 3 by 2. Now for small displacements, x is much lesser than r, I can ignore the x squared in the denominator, and therefore the force will come out to be. So you can see for small displacements, the force is proportional to x, and therefore my time period would simply be 2 pi root m by k equivalent, and the k equivalent is the constant of proportionality between force and k, force and x rather. So this will be mr cube divided by. So this will be your time period. So it's a straightforward question. You just have to know what to neglect. And of course, there should be a negative sign here because remember Q is negative. Q is negative, and therefore there's already a negative sign here inside Q, and therefore K equivalent here, basically K equivalent would be KQQ by R cube with a negative sign. So this is your proportionality constant between force and displacement. Now one more case that we should look at is if the ring were free to move. So if the ring were free to move, then this becomes a two-body SHM. So in two-body SHM, we know the time period is 2 pi root mu by K equivalent. This is a standard formula that you should know from your study of SHM, where mu is the reduced mass. So mu here would be mm dash divided by m plus m dash. This is your reduced mass, and K equivalent will simply be this thing. So all you have to do is substitute K equivalent here, and instead of mass m, you use the reduced mass. So basically, all you need to do is to recognize which system is a two-body SHM. Once you do that, then it's very straightforward. Alright, let's do another question. A thin rod of mass m carrying uniform negative charge minus q, so this entire rod is carrying minus q, is placed symmetrically along the axis of a thin ring of radius r, carrying uniformly distributed charge capital Q. So the ring has uniform charge distribution of capital Q. The ring is held fixed in free space, and the length of the rod is 2r. So this entire length is 2r. Find the period of small amplitude oscillations of the rod along the axis of the ring. So if I just displace the rod by a small amount along the axis, then what will be the time period? So let's take a look at this question, and if you want, you can pause the video and try it out on your own, and then you can take a look at my solution. Alright, so I have this ring and I have the rod of length 2r. Now if I were to just displace this rod by x, now the question says it's in free space, so there's no concept of gravity here. If I were to displace the rod by a small amount of x, the length above the ring is going to be r minus x, and length below the ring is going to be r plus x. So now I need to find out the force on this rod, and that force will hopefully come out to be proportional to x. We may need to make an approximation, and then once we have that, we have the proportionality between force and x, then it's an SHM, then it's pretty straightforward. Now how will we calculate the force on this? One long way is to integrate from the top point to the lowermost point, integrate the electric field of the ring, but we don't need to do that, because if I look at a section, see this blue section is r minus x, if I just look at another r minus x below, then their forces will cancel out, because the ring will be attracting the upper section downwards and ring will be attracting the lower section of r minus x upwards. So the net force will cancel out on these two blue sections. What we will remain is with this section of length 2x. So this green portion is the portion on which the force on this green section will become the net force on the entire rod. So now it's pretty straightforward. In order to calculate this force on this green section, see, we are displacing it by a very small amount. So we can treat this green section as a very small length, almost like a point charge. So if I look at the distance from the axis to the center of the green section, that is nothing but simply r. And therefore the force on the green section, which will also be the net force on the rod, is going to be KQ into the charge of the green section. How much charge will be on the green section? The entire rod has a length of 2r. So entire length of 2r has minus q charge. So 2x will have how much charge? Just basic unitary method. So now that we have the charge of the green section, I can find the force on the green section as electric field of the ring multiplied by the charge. So what will be the electric field at a distance r? So that will be KQ in the distance r divided by r square plus once again r, so r square raised to 3 by 2. So this is the electric field of a ring. I've just used the formula of electric field due to a ring on its axis multiplied by the charge of the green section. So I'm just going to write the magnitude, because I know that the direction of the force is in the upward direction. It will be an attractive force. So this will come out to be KQQ divided by 2r cube times x. So this is SHM. Oh, there should be a root 2 here. Okay, so this is my k equivalent, and therefore my time period would simply be 2 pi root m divided by k equivalent. So 2 root 2 mr cube divided by k cube cube. So this will be your time period. Now let's look at the electric field due to a disk. So uniformly charged disk, the electric field, let's say the charge density on the disk is sigma. So sigma is charge per unit area and it is uniform. So on its axis, at any point, if the disk subtends a half angle of theta, the electric field is going to be sigma by 2 epsilon naught into 1 minus cos theta. So it is something that we must remember. And if I assume that this disk is infinitely large, so that basically means an infinite sheet. For an infinite sheet, the shape of the boundary doesn't really matter. So even if I assume this sheet is like a disk whose radius is tending to infinity, the shape of the sheet is irrelevant. So for an infinite sheet, I can simply set theta tending to 90 degrees. You can just imagine as the radius of the disk increases, theta will keep on increasing here, and ultimately as r becomes infinity, theta will tend to 90 degrees. And just substitute theta 90 degree in the field of the disk, and you will get the electric field due to a sheet, which is sigma by 2 epsilon. So just remember. Alright, now let's come to potential. So electric potential is defined as in the same way that electric field was defined for a charged object. If you want to write the potential at some point, at point P, we bring a test charge there, we place a test charge, write the potential energy between the charged object and the test charge, and divide it by the test charge. So that will give the potential due to the charged object. This is at point P. So there will be no mention of Q dash. It will only be a property of the charged object itself and of course the distance from the charged object. For a point charge, the potential comes out to be kq by r. At a distance r from the point charge, you can see the potential will be positive if the point charge is positive, and potential will be negative for a negative charge. Now let's look at the potential due to a ring. So due to a ring on its axis at a distance x from the center, the charge is q. So this distribution may be uniform or non-uniform. This is something that is important. So the distribution doesn't really matter. The reason is because every point charge on the circumference of the ring, let's assume a dq charge, has the same distance of root of r square plus x square from this point P, where I want to find the potential of the ring. So if I write the potential of the ring as the sum of potentials due to individual point charges, I just have to integrate. You can see that all of this is a constant, and you will end up with simply integral of dq. Here we have not assumed anything about the distribution of the charge, so that may be uniform or non-uniform. So this will be the potential due to a ring, whether the distribution is uniform or non-uniform. The relation between electric field and potential is that you can write the x component of electric field as minus del V by del x. This is the same relation as force and potential energy. Y component as minus del V by del y, and similarly for z component. So here, if I were to just differentiate this potential of the ring, I will get kqx divided by r square plus x square raised to 3 by 2. You'll get the x component. Now we do not know how the potential varies on points that are not on the axis. So therefore we cannot do any calculation for Ey. But if the ring is non-uniformly distributed, the charge is non-uniformly distributed, then Ey may come out to be non-zero. If the ring is uniform distribution, then Ey will automatically be 0, Ey Ez will automatically be 0 just by symmetry, and this will be the entire field that we already saw. Now let's take a look at a question. I have two rings, concentric and in the same plane. So the inner ring is charged, let me call it ring 1 and ring 2. So radius of ring 1 is R, and it is charged with, uniformly charged with charge Q, and for ring 2 the radius is 4R, the charge is minus 8Q. So ring 2 is negatively charged, Q here is positive, and I have a particle of mass m and charge minus Q from infinity, and it's projected with velocity v0. So the question is asking us, find the minimum value of v0 such that the particle reaches the centers of the ring, center of the rings. Okay, so here we have to be a little careful because I have two rings here. So ring 1 is positively charged, which will be attracting the particle, and ring 2 is negatively charged, which will be repelling the particle. So in such questions, what you need to do first is figure out if there exists a position of unstable equilibrium. Suppose you have an unstable equilibrium here. If the particle is able to cross this point, then it will on its own get attracted towards the center. That is the definition of unstable equilibrium, that if you displace it slightly away from the unstable equilibrium, the force will carry it away. So we need to figure out if an unstable equilibrium exists. So for that, first we need to figure out where the equilibrium position is, and then we'll check its stability. So if you want, you can pause the video right now and try it out on your own, and then you can take a look at the solution. Okay, so for the equilibrium position, we'll need the electric field of 1 and 2 to result in a 0 value. So let's say at a distance x, the electric field of 1, let me take right hand side as positive, so electric field of 1 will be towards the right, 1 is positively charged, and that will be kqx divided by r square plus x square raised to 3 by 2. And electric field due to ring 2 would be k, the charge is minus 8q times x divided by, now radius is 4r, so 4r the whole square plus x squared raised to 3 by 2. Alright, so I'll need E1 plus E2 to be 0 for equilibrium position. And obviously one equation is x is equal to 0, which is the center, which is obvious. But we don't want that. We want to look at if there exists any other equilibrium position on the axis. So let's just take a look at that. So kq divided by r square plus x square raised to 3 by 2 minus 8kq I've just cancelled out this x when I added them and equated it to 0. Alright, so I'll have 4r the whole square plus x square raised to 3 by 2 should be equal to 8 times r square plus x square raised to 3 by 2. So obviously 8, I can write 8 as 4 raised to 3 by 2. So let me just take this 8 inside. So I've just taken that 8 inside the bracket, and now I can just equate. So I'll have 4r the whole square plus x square should be equal to 4r squared plus 4x squared. So I'll get x squared, or rather x, as 2r. Now we need to check if this equilibrium position is stable or unstable. So one way of doing this is if we can calculate the slope of the electric field, if I can calculate the slope of the net electric field, and if it comes out to be positive, that means slope of the force will be negative because the charge is negative. You'll have to check this derivative at x equal to 2r, but this is a little long method because you'll have to differentiate E1, E2 and substitute x. Rather, we will use the result that the field of a ring is maximum at r by root 2. So, and from the graph, we'll be able to quickly figure out the slope of the electric field. So let's just do that on the next page. I know that the electric field this is r by root 2. This is the electric field of a ring charged with q and radius r. And the electric field due to the ring of radius 4r is a negative. So the electric minus 8q, the electric field will be in the negative x direction. So it will be something like this. The maxima will come out to be 4r by root 2. Now, where is our position of equilibrium? That is at 2r. So 2r will be somewhere here. Now at 2r, the net field is going to be the sum of this black curve and the red curve. The black curve is due to the positively charged ring and the red curve is due to the negatively charged ring. The resultant of those is the net electric field. But can you see that the slope at 2r is negative for both the red curve and the black curve, and therefore for the net electric field the slope is negative, and therefore df by dx will be positive because force is charge times the electric field and the charge of the particle is negative, and therefore this implies that this is unstable equilibrium. So now our question is pretty simple. Now we have to simply ensure that the particle reaches this unstable equilibrium position. After that, the electric field will automatically carry it towards the left and make it reach the center. So what I'm going to do is I'm going to set the velocity to be just 0 at x is equal to 2r. So we just conserve energy. Initial energy is simply the kinetic energy because it's at infinity, potential energy will be 0. And at x equal to 2r, the kinetic energy is 0. We've just set the velocity to be 0. And what about the potential energy? That will be the potential times the charge. So what is the potential due to the first ring? Kq divided by r square plus x square, x is 2r. And what about the potential due to the outer ring? That will be k times minus 8q divided by root of 4r the whole square plus times minus q. So this is the potential due to both the rings at x equal to 2r times minus q. I've just used the formula for the potential of a ring that we saw earlier. Oh, there should be a positive sign here. I've already included the negative sign and the charge of the negatively charged ring here. Alright, so just solve for velocity and you will get it as 6kq squared by root 5 mr, square root of that. So this will be a velocity of the particle. Now let's look at the potential of a disk. So at a distance x, let's say radius r, at a distance x on the axis, the potential comes out to be sigma by 2 epsilon naught root of r square plus x square minus x, where sigma is the charge per unit area. It's a uniformly charged disk. So this is my potential. Here the derivation for this potential comes from either one way is to integrate the potential of rings that you can imagine the disk to be made of, or you can integrate the electric field of the disk in order to get the potential. The relation between potential and electric field is dV minus E dot dr. So you could integrate this to get the potential. Now let's look at a question. So let's say I have an infinite sheet and sigma is the uniform charge per unit area, and let's say I have a circular disc cut out. So my sheet is only this much, the circular part is cut out, and let's say that circular portion that is cut out has a radius r, and at a distance of root 3r there is a particle. So let's say sigma is positive and this particle has a mass m and a charge minus q. So this particle is negatively charged and it's on the axis of the circular portion which is cut out. So the question is asking Find the speed of the particle when it crosses the center of the sheet and the charge is released from rest. Right, so think in terms of energy and give it a try, then you can take a look at my solution. Alright, so I can treat this sheet with the cutout circle as an infinite sheet minus a circular disc. So I know the potential due to the circular disc, I even know the field due to an infinite sheet, so that's what I'm going to use. So firstly, can I write work energy theorem that the work done by electric field should be equal to change in kinetic energy? Now work done by electric field, I'm going to write it work done by the infinite sheet minus work done by the disk, because my situation can be treated as the infinite sheet minus the disk. So this should be equal to change in kinetic energy. So work done by sheet is very easy to write because the field is a uniform field. Can I write work done by the sheet? By sheet here I mean the entire infinite sheet. So this would simply be the electric force multiplied by the displacement. Now the electric force on the minus q charge will be towards the left. Sigma is positive, so electric field will be to the right and the charge is negative. And the force would be sigma by 2 epsilon naught times q. This is the magnitude of the force and the displacement is root 3r. So work done by the sheet, by the electric field due to the sheet would be sigma q by 2 epsilon naught times root 3r. Now work done by the disk, can I write it as negative of change in potential energy? In potential energy, I can write it as charge times potential. So can I write it as the charge times the change in potential? So final potential minus initial potential. This is all due to the disk and with a negative sign here, because work done by the disk will be negative of the change in potential energy. Alright, so what is the final potential? So final potential, I'll have x is equal to 0 because the particle will be at the center of the circle. So if I look at this formula for the potential of the disk that we got, I'll have, if you substitute x equal to 0 here, I'll simply get it as sigma by 2 epsilon naught times r. This will be the final potential. Q times sigma r by 2 epsilon, this will be the final potential minus, so what's the initial potential? For initial potential, I'm going to have to substitute x is equal to root 3r. So once again, I'll substitute x equal to root 3r here. So I'll have sigma by 2 epsilon naught. This will r square plus x square will become 2r minus root 3r. So this will be the initial potential. So let's just substitute that. So initial potential was sigma by 2 epsilon naught times 2r minus root 3r. Alright, now I'm going to simply substitute work done by the sheet and work done by the disk here. And I'll equate it to half mv squared, which is the final kinetic energy. Initial, the particle was at rest. And so I'll get velocity as q sigma r by m epsilon naught, square root of that. So this is the velocity that you'll get for the point charge. Now let's come to the concept of electric field lines. So electric field line is a curve whose tangent at any point gives us the direction of electric field at that point. So if you consider the case of 2 point charges q and minus q, the electric field line goes from positive charge to negative charge. Oh, these arrows should be inwards here. These field lines will be going into the negative charge. I had mistakenly drawn them away from the negative charge. Alright, and what if the charges are of the same sign? So then the field lines will repel each other. So I have assumed two positive point charges here. The field lines will be repelling each other. You'll have, of course, zero field at the center. And this will be your electric field lines for this configuration. Electric field lines are very closely related to the concept of flux. So if you have different magnitudes of these charges, then we'll talk more about that when we study flux. Alright, let's also talk about equipotential surfaces. So equipotential surfaces are surfaces whose potential at every point on that surface is a constant. So for example, if I have a simple point charge, at a distance r the potential is equal to kq by r, and if I set it to a constant, I'll get r as a constant, which in 3 dimension is basically a spherical surface. So these will be your equipotential surfaces. And an important property of equipotential surfaces is that they are perpendicular to the electric field lines. The electric field lines are normal to the equipotential surface. So they are perpendicular to the electric lines of force or electric field lines. Electric lines of force go from higher potential to lower potential. Something that we should remember. And this is due to the fact that the change in potential is given by minus E dot dr. So if dr is a displacement along E vector, if you choose to travel along the electric field vector, you can see that dv will be negative because E dot dr will be positive. So as you go along the electric field line, the potential will drop. So in this case, as we all know, the electric field lines are radial, so they will be perpendicular to the equipotential surfaces, and they will be going away from the point charge. And that also means they will be going from higher potential to lower potential. The further away you go from the positive point charge, the potential will decrease. Now let's look at a question. So let's say I have my electric field as a function of xy coordinates in space given to us as some constant c times yi cap plus xj cap. C is a constant, let's say positive constant. And I want to find the equation of the field lines. And let's say equipotential surfaces as well. In the xy planes. So even though the equipotential surface will be in three dimensions, it will be a surface in 3 dimensions. We only want the projection of the equipotential surface in the xy plane. We want the equation of that. So let's take a look at how we can do that. So the field line, remember, is a curve whose tangent gives us the direction of the electric field. So any slope of a general curve in the xy plane will simply be dy by dx. Now this should have the same slope as that of the electric field. So electric field, basically the slope of a vector will simply be the y component by x component, and here the y component is c times x and the x component is c times phi. So this will become x by y. And now all I have to do is integrate. So I'll have y dy is x dx, and I'll just perform indefinite integration. So I'll get x squared, y squared by 2 is equal to x squared by 2 plus some constant. So let me write it that way. So this will be a general family of electric field lines. What about the equipotential surfaces? So the equipotential surfaces, we remember, are perpendicular to the electric field lines. So for the equipotential surfaces, I can write dy by dx. Remember, the product of slope of two perpendicular lines is -1. That's what you've studied in mathematics. So dy by dx here will be equal to minus y by x, inverse of the slope of the field lines and with a negative sign. So once again, this is a simple integration. Perform indefinite integration. I'll have ln y is minus ln x plus some constant. So ln xy is a constant. Therefore xy is itself a constant. So this will be the equation of the projection of the equipotential surfaces in the xy plane. Let's talk about dipoles. So a dipole consists of a negative charge and a positive charge. Let's say this is d vector. So this vector is pointing from minus q to plus q, and we define something called dipole moment as q times d vector. So this is the definition of the dipole moment. So in questions, they may ask you to find the dipole moment of more than just two charges. So if a system is neutral, they can ask you to find the dipole moment of that system. So for example, if I have, let's say, three charges, let's say this is 1 coulomb, 2 coulomb and minus 3 coulomb. So they can ask you, this is a neutral system, so they can ask you to find the dipole moment of this system. And in such questions, what you need to do is you need to find or split this system into pairs of minus q and plus q. Magnitude of the pair of charges should be equal, the signs should be opposite. So we are basically breaking down the system into individual dipoles. So if I select any, just choose any one of the charges, that is up to you. So let me just select minus 3 coulomb and let me split it into minus 2 and minus 1 coulomb. So I'm going to split 3 coulomb into minus 2 and minus 1. And then I'll say that minus 1 and 1 form a dipole moment. Let's say P1 vector. And minus 2 and 2 form another dipole moment, P2 vector. So if you know the distance between, let's say this is R1 and let's say this is R2. So the magnitude of the dipole moment would be 1 times R1 and magnitude of P2 would be 2 times R2. And then of course, if you know the angle, you can get the dipole moment vector by just taking the vector sum of 1 and 2. Now, if I had chosen 1 coulomb and if I chose to split 1 coulomb into two charges, let's say 3 coulomb and minus 2 coulomb. And if you group 3 coulomb with minus 3 coulomb and 2 coulomb with minus 2 coulomb and you found out the resultant dipole moment, you will get the same answer. So it doesn't matter how you split the charges, you will get the same answer. Another useful type of method here is, let me show you by an example. Suppose I have a ring and let's say half of the ring is uniformly charged, the other half is charged with negative charge. So lambda and minus lambda are the charge per unit lengths. Now I want to find the dipole moment. This is overall neutral, but I want to find the dipole moment of this ring. So one way is to just imagine this ring to be made up of lots of infinitesimal dipole moments. It could be this way or it could even be radial. And then you'll have to integrate, but the fastest way is to replace the individual semicircles by the center of mass, by the charge at the center of mass. So center of mass of a semicircle is at 2r by pi. So I'm going to replace the positive half by a point particle at 2r by pi and the negative half by a point particle minus q also at 2r by pi. Now what is this charge? So q is the charge on the semicircle, so that will be lambda into pi r. Pi r is the circumference of the semicircle, and therefore my dipole moment will simply be q times d, where d is the distance between q and minus q, so that will be 4r by pi. So you can just substitute q as lambda pi r and you will get it as 4 lambda r square. So this will be the dipole moment of this ring, and you could even get a question where you have, instead of a ring, you could have a disc where each half is given a positive charge and a negative charge. So once again, just replace the charges by point particles at the center of mass and get the dipole moment, or it could even be a sphere. So whatever the case is, just remember this method. It will save you a lot of time instead of doing any sort of integration. Now let's talk about force on a dipole. So if you have a dipole placed in an electric field, and suppose that electric field is uniform, then the force will be 0, because you will have equal and opposite forces on the positive charge and the negative charge, equal in magnitude and opposite in direction. And the force of the dipole will be 0, but they will form a couple. So I'll have a QE force here and a minus QE force here. So this will form a couple. So couple is a pair of forces which are equal in magnitude and opposite in direction. So there will be a torque, and that torque comes out to be P cross E. So this torque is the same at any point. that is the feature of a couple. The torque of a couple about any point is the same. So torque here comes out to be equal to P cross E. And we can even define a potential energy for a dipole in a field which is equal to minus P dot E. So these are things that we should remember. Suppose the dipole is placed in a non-uniform field. In that case, the force is not zero. Instead, it comes out to be equal to P dE by dl. So here, L is, or rather dl is the distance between minus q and plus q. I am assuming a small dipole. So here we've all assumed small dipole. What is dE here? dE is the change in electric field, or rather let me just write it as electric field at the positive charge minus electric field at minus q. So it's the change in electric field as you go from minus q to plus q, and dl basically represents the distance between minus q and plus q. So notice that the force vector is in the same direction as dE vector. That is something that you should realize. So let's take a look at an example. So suppose I have an infinite wire. Let's say charge per unit length is lambda, and at a distance r, I have a dipole kept in this manner. So it's a small dipole at a distance r, and I want to find out what is the force on the dipole. So I know the electric field. Can I write it? Let me just say this is I cap. Can I write my electric field due to the infinite wire? Let's assume it's positively charged, so that will be 2k lambda by r I cap. So we know this from the field of a line wire, and therefore the force vector on the dipole will simply be P dE by dr. So dE by dr would be so this will be your force vector, and notice that you're getting a negative sign here. So force is along minus I cap, and that makes sense because if I look at the dipole, that is nothing but a minus sign and a positive sign charge. So the negative sign is closer to the line wire, so it will experience greater attraction than the positive charge of the dipole. So the net force on the dipole will be an attractive force, and that is what this minus sign is telling us. Let's do another example. Suppose same infinite line wire, let's say charge per unit length is lambda, and at a distance r, I place a dipole parallel to the line wire. Now can you figure out the force? So just take 2 minutes, it's a very straightforward question, and you probably don't even need to do any calculation. Just take 2 minutes, pause the video and try it out. Alright, so you should have gotten that the force on this dipole is 0. And even if you do not do any sort of calculation, you should be able to see that I have a minus q charge and a positive q charge, and the electric field is the same on minus q and plus q both. They are both at the same distance from the line wire, and therefore the net force will be 0 because plus q and minus q will experience the same magnitude of force but in opposite direction. Now let's look at a slightly different example where the dipole is placed perpendicular to the line wire but perpendicular to the plane of the screen. This is my dipole moment. If I look at the top view, let me say this is, let me mark the line wire by blue, let me mark the dipole by red. So dipole is pointing inwards. So the top view, this will be my line wire and this will be my dipole moment. Alright, so I want to find the force on the dipole moment. So if you want, this is a slightly different problem, but if you want, you can pause the video and try it out on your own. Okay, so if I look at my force vector, so force, what was force? Force was P times dE by dl. Now remember, dE vector is the change in electric field as you go from the negative charge to the positive charge of the dipole moment. So let's say my dipole moment, let's say is minus q and plus q. So this is dl. Let's say this angle is d theta. Alright, so let's say first I want to find what is dl and then I'll find dE vector. So for dl, if I look at this triangle, this is r, This is d theta by 2. This is also d theta by 2. So you should be able to see that dl, I can write it as 2r tan d theta by 2, just from the triangle. And I know tan x can be written as x for small x, so this will become r d theta. Alright. You could have even written this directly. So further, I did this explanation in order to show you in detail how we get r d theta, but from now on you should be able to write this directly, that if I have a vector that is rotating from, that is only rotating, let's say from minus q to plus q, this r vector is rotating by d theta, then the arc length dl becomes like the arc length, and you should be able to directly write it as r d theta. So in the exam, don't bother doing this. You should be able to write that as r d theta. Now, in a very similar manner, if I have electric field, say electric field will be radially away from the line wire. So my electric field at minus q is this way and at plus q is this way, and the angle is d theta. So what is the change in the electric field? Once again, the electric field is rotating by d theta, and using the same logic, I can write dE as e d theta. Just remember that any vector, if it rotates by d theta, the change in vector, the magnitude would be a d theta, because that becomes like the infinitesimal arc length as the vector rotates. So this is just a general thing that you should know. Alright, so now it's very straightforward. I know dE is e d theta. And what is electric field? The magnitude of electric field is simply 2k lambda by r. And I know dl is r d theta. So all I have to do is substitute it here, and the force would be equal to P times d theta divided by dl, which is r d theta. So this will be 2kp lambda by r square. So this will be the magnitude of the force. And what about the direction? So the force vector is in the direction of dE vector. So I know that my initial vector is this way, or the electric field at minus q is in this manner, and electric field at plus q is in this manner. So I need to subtract electric field at plus q minus electric field at minus q. So just basic vector subtraction, you should be able to see that dE vector would be in this manner, this way. So the force will be parallel to dE vector, and therefore parallel to the dipole. So the force will be parallel to the dipole. Let's do another question. So suppose I have a ring, uniformly charged ring. Let's say charge is q, radius is r, and on its axis I have a dipole, small dipole, placed at a distance x. So what I want to do is I want to find the value of x such that the dipole is in equilibrium and its stability with respect to displacements along the axis. So the question is asking us to find the location of the equilibrium position of the dipole, and if you displace the dipole along the axis, then whether that equilibrium is stable, unstable, what kind of stability it is, that is what the question is asking. So I would suggest that you pause the video and try it out on your own. Alright, so first thing, the force on the dipole, I know it will be equal to P dE by dx. Now what is the electric field due to the ring? That is something that we already know, kqx divided by r square plus x square raised to 3 by 2. So this force should be 0 for the equilibrium position, and we know where the electric field derivative is 0 for the ring. Basically that corresponds to the maxima, the position of maxima of the electric field for the ring, which you should remember. So you could either differentiate this and get the value, or I would suggest that you should remember that anyway. It comes out to be equal to r by root 2. So this is the position of the equilibrium for the dipole. Now let's discuss the stability as well. So for stability, I will need to calculate dF by dx. If that is positive, then the equilibrium will be unstable, and stable if it is negative. So dF by dx basically means P times d to E by dx square. Now I already know that at x equal to r by root 2, this corresponds to the maximum of the electric field. So at the maxima, the double derivative is negative. So So we know that from calculus that the double derivative at the maxima is negative, and therefore df by dx will be negative, and therefore this equilibrium is a stable equilibrium position. So I hope you've understood how we solve this question. It's very straightforward, provided you know, or rather remember, the position of the maxima of the ring. Now let's look at the field of the dipole and the potential produced by the dipole. So I'm going to use a small dipole, or I'm going to use, or rather look at a point which is very far away from the dipole. So let's say point P is very far away. So far away mathematically means that this distance from the center of the dipole is r, and let's say this is distance d. I know dipole moment is q times d. So r is much greater than d. So at that point the potential comes out to be kp cos theta by r squared. We should remember this. And the electric field, so what I can do is I will define polar coordinates. So I'm going to define r cap and theta cap. So r cap is the unit vector pointing away from the dipole along r, and theta cap is perpendicular in the anticlockwise sense. So anticlockwise sense meaning, just imagine that you have a circle here centered at the dipole, and theta cap is always in the anticlockwise sense. So at this point my r vector would be this way, r cap would be this way, theta cap would be this way. So these are my unit vectors. So the radial and the tangential component of the electric field, ER, comes out to be minus del V by del R. So you're differentiating with respect to R while keeping theta as constant. So this will come out to be 2 kp cos theta by R cube, and E theta would be minus del V by R del theta. So this will be kp sin theta by R cube. So these will be your components, the radial and the tangential. You should be able to either remember them or be able to derive the field components from the potential. Alright, so let's do a question. So I have a dipole, a small dipole which is fixed, and I have a smooth fixed railing and no gravity, and I have a bead of charge q which is slightly pushed in the upward direction. So the question is asking, find the speed of the bead when the normal force between the bead and the railing becomes 0. Alright, so try it out, just pause the video, try it out, and then you can take a look at my solution. Okay, so let's say that the normal force between the bead and the railing becomes 0 at this angle theta. So what will be the forces? So I have my electric field in this manner, ER, E theta. So the forces would be QER and QE theta. This angle is theta. And the normal force becomes 0. So the bead anyway has 0 acceleration in the, let's say this is the x direction and this is the y direction. So in the x direction the bead has anyway 0 acceleration because the bead can only move in the y direction along the railing, and therefore the forces in the x direction should cancel out. So can I write QER cos theta should be cancelling out QE theta sin theta. So these are the x components of QER and QE theta. Alright, so we'll just substitute ER. We found that out to be 2 kp cos theta by r cube should be equal to E theta was kp sin theta by r cube. So basically I'll have tan square theta is 2. So let me just write tan theta as root 2. Alright, now at this particular angle theta we want to find the speed of the bead. So we can conserve energy. So let's do that on the next page. So initially the kinetic energy of the bead was 0 because it was given a slight push, so negligible velocity. And what about the initial potential energy? So initially the bead was here on the x-axis. So I can write the potential energy of the bead in the presence of the dipole as q times the potential, and the potential is kp cos theta by r squared. So initially theta is 0. So I'm going to substitute theta as 0 initially. So this will be simply kpq by r squared. So r here is L, so L squared. Alright, what about the final position here? So first of all, this length would be L sec theta. So the final potential energy would be Q times Kp cos theta divided by R square. So R would be L sec theta. So L square sec square theta. Alright, what about theta? So we had theta as tan theta is root 2. So can I write cos theta as 1 by root 3? And therefore the final potential energy would be Kpq by L square. So I have here cos cube theta. So that will be 3 root 3 in the denominator. So this will be our final potential energy. So now I'll just conserve energy. So Kpq by L square is the initial energy of the bead. Finally, it's Kpq by 3 root 3 L squared plus kinetic energy is half mv square. And therefore, I'll get v, the speed of the bead. That is what the question is asking. So I'll get that as, you can just do the calculation on your own. This will be the speed of the bead. So I hope you've understood how we solve this question. This question is a very nice question because it required us to have the knowledge of the electric field of the dipole as well as the potential due to the dipole. So that's why I chose this particular question, which involves all the concepts together.